The Barents Sea is a place of brutal, unyielding physics. Locked in the Arctic Circle, its waters are characterized by extreme density, near freezing temperatures, and a seabed composed of ancient, compacted glacial silt. On the 12th of August 2000, this environment became the final resting place for the K-141 Kursk, an Oscar II-class nuclear-powered cruise missile submarine. When it struck the seafloor at 108 meters, it wasn't just a shipwreck. It was 154 meters of high-tensile steel driven into a thick, clay-like mud, creating a suction bond that many Russian naval architects believed was unbreakable. The Oscar II class was the pinnacle of Soviet naval engineering, a vessel so massive it could stay submerged for 120 days and carry enough firepower to level a coastal city. It featured a unique double-hull construction. The inner pressure hull was built from high-yield, 1.5 to 2-inch thick steel, while the outer light hull acted as a hydrodynamic shell. This hull-within-a-hull design created a 2-meter void that absorbed shock and made the submarine nearly silent. However, following the catastrophic detonation of its torpedo room, this design became a liability. The explosions had ripped through the first 4 compartments, turning the bow into a jagged, structurally unstable mass of twisted girders and unexploded ordnance. For the international community, the Kursk was more than a tragedy. It was a global security threat. The vessel carried 2 VM-4 pressurized water reactors, each producing 190 megawatts of power. While the reactors had automatically shut down, they were now sitting in a corrosive saltwater environment with their cooling systems compromised. Additionally, the ship was armed with 24 P-700 Granite SSN-19 shipwreck supersonic missiles. These missiles were designed to carry 750 kilograms conventional warheads, or 500 KT nuclear payloads. The stability of these weapons after a massive internal explosion and a 100-meter descent was entirely unknown. The Russian government initially maintained that a recovery was impossible. The sheer scale of the ship displacing 18,000 tons when submerged dwarfed any existing salvage equipment. Furthermore, the suction effect of the Barents Sea floor meant that any attempt to lift the ship would require overcoming a breakout force estimated at nearly double the vessel's dry weight. Conventional wisdom suggested the Kursk would have to be cut into small pieces underwater, a process that would take years and risked a catastrophic radiation leak if the reactor compartment were breached. Despite these warnings, a plan emerged that would push the limits of maritime engineering. The Russian Federation reached out to the Dutch firm Mammoet, known for moving the world's heaviest industrial objects. The proposal was radical. They wouldn't cut the Kursk into pieces. They would lift the entire 9,000-ton remaining hull in a single, vertical pull. This mission would require the total modification of a semi-submersible barge called the Giant 4. The barge had to be transformed from a simple transport vessel into a sophisticated lifting platform capable of maintaining sub-millimeter precision in the middle of an Arctic gale. The engineers were fighting against a ticking clock. The weather window in the Barents Sea is notoriously short. If the lift wasn't completed before the October storms, the Giant 4 would be torn apart by the very vessel it was trying to save. The first step in this impossible lift wasn't the pull itself. It was the surgery. The bow of the Kursk, which was buried deep in the silt and riddled with unstable torpedoes, had to be removed. This was done using a custom-engineered diamond wire saw. This device consisted of a massive frame that straddled the submarine, driving a cable studded with industrial diamonds through the double-hull steel. It was a process of agonizing friction. If the saw hit an unexploded torpedo or a high-pressure air flask, the resulting explosion would likely destroy the salvage equipment and any divers in the vicinity. As the saw ground through the 18,000-ton Titan, the engineering world watched with bated breath. This was a confrontation between modern Western technology and the legacy of Soviet military might, played out in one of the most hostile environments on Earth. The successful removal of the bow was the first proof of concept, but it led to an even greater challenge. How do you grab 9,000 tons of smooth, rusted steel and pull it through 100 meters of water without it snapping in half? To lift the Kursk, the Dutch engineers at Mammoet and Smit International had to solve a fundamental problem of physics, the heave of the ocean. A standard barge sitting on the surface of the Barents Sea is subject to the constant vertical motion of the waves. If the barge is tethered to a static 9,000-ton object on the seafloor, every time the barge rises on a swell, the tension on the cables would increase exponentially. At those scales, The steel cables wouldn't just stretch, they would act like a whip, snapping with enough force to liquefy anything in their path or instantly shearing the submarine's hull. The solution was the total transformation of the Giant 4, a 140-meter-long semi-submersible barge. The team installed 26 massive strand jacks on its deck. Unlike a traditional winch that uses a single thick cable, a strand jack utilizes a bundle of high-tensile steel strands. Each jack on the Giant 4 controlled a bundle of 54 individual strands. These jacks were controlled by a centralized computer system that synchronized their movement to within a fraction of a millimeter, ensuring that the 9,000-ton load was distributed perfectly across the barge's structural frame. To handle the North Atlantic swells, each strand jack was paired with a heave compensation system. These were essentially giant hydraulic pistons, pressurized with nitrogen. As the barge rose on a wave, the pistons would extend, giving line to the submarine. As the barge sank into a trough, the pistons would retract. This allowed the submarine to remain perfectly stationary in the water column, while the barge moved violently above it. It was a masterpiece of active damping, maintaining a constant tension of approximately 350 tons per lifting point. The anatomy of the connection. The most harrowing technical challenge was the grab. You cannot simply wrap a chain around a nuclear submarine. The outer hull of an Oscar II is relatively thin and covered in rubber anechoic tiles designed to absorb sonar. To lift the ship, the engineers had to anchor directly into the inner pressure hull, the high-strength steel cylinder that protects the crew from the crushing depths. Working in near-zero visibility, divers and ROVs used high-pressure water jets to cut 26 precise circular holes into the top of the submarine. These holes had to be positioned with surgical accuracy between the submarine's internal bulkheads and the massive P-700 missile tubes that lined the sides of the vessel. Once the holes were cut, the lifting plugs were lowered from the Giant 4. These were massive, custom-forged steel cylinders equipped with a toggle or expanding head. Once the plug passed through the hole in the pressure hull, a hydraulic mechanism triggered the head to expand, locking it against the underside of the 2-inch thick steel plate. It was essentially a 9,000-ton version of a toggle bolt used to hang a heavy mirror on a wall. The suction breakout. By October 2001, the 26 plugs were seated. The weather was deteriorating, with the Arctic winter closing in. The engineers now faced the most unpredictable variable of the mission: seabed suction. When a vessel as heavy as the Kursk sits on a clay seabed for over a year, it creates a vacuum seal. To lift the sub, the strand jacks had to exert enough force to not only overcome the 9,000-ton submerged weight, but also the thousands of tons of atmospheric and hydrostatic pressure pinning the sub into the mud. The tension was increased slowly. The computer readouts showed the load climbing: 5,000 tons, 7,000 tons, 10,000 tons. The Giant 4 itself began to sit lower in the water, its own buoyancy being sacrificed to generate the upward pull. For hours, the submarine didn't move. There was a very real fear that the hull might simply snap, leaving the midsection in the mud and bringing only the top half to the surface. Then, a sudden drop in tension was recorded on the sensors. The seal had been broken. Water rushed into the void beneath the hull, and the Kursk was finally free. The nuclear transit. As the Kursk was slowly winched toward the surface, the technical focus shifted to the reactor compartment. The two VM-4 reactors were located in the fifth compartment, which remained largely intact. However, the shock of the initial explosions and the stress of the lift could have cracked the primary cooling loops. The engineers had to ensure the submarine remained level within 1.5 degrees. Any significant tilt could cause the heavy lead-bismuth shielding or the fuel assemblies within the reactor to shift, potentially leading to a criticality event, a localized nuclear reaction. To prevent this, the Giant 4 had been designed with a cradle on its hull. As the Kursk reached the surface, it was pulled directly into a custom-shaped recess on the underside of the barge. This turned the barge and the submarine into a single, rigid hydrodynamic unit. The submarine was no longer hanging. It was now part of the barge itself. On the 10th of October 2001, the Giant 4, carrying its 9,000-ton nuclear passenger, began the slow trek toward the Roslyakovo shipyard. The world watched a ghost ship rise from the depths, a rusted, jagged testament to the dangers of the Cold War and the triumph of modern engineering. The transit to the Roslyakovo shipyard was a 600-mile journey through some of the most treacherous waters on the planet. The giant four moved at a crawling pace of 4 knots. The engineering team remained on high alert. The Kursk was still live. Its hull contained 22 P-700 granite missiles, and while the reactors were stable, they were now being subjected to different pressures and orientations than they had experienced in over a year. Upon arrival at the shipyard, a new engineering challenge began: the docking. This wasn't a standard dry dock procedure. The Kursk was still nestled in the belly of the giant four. To separate them, the massive PD-50 floating dry dock, one of the largest in the world, had to be submerged. The giant four was then floated over the submerged dock. As the water was pumped out of the PD-50's ballast tanks, the dock rose, lifting both the barge and the submarine simultaneously. Only once the water was fully drained did the world see the true scale of the devastation. The first 20 meters of the submarine were gone, sawn off, and left on the seafloor. What remained was a blackened, silt-covered cylinder of steel, twisted by internal pressures that had reached thousands of pounds per square inch during the explosion. The missile threat. Before the forensic teams or the recovery divers could enter the hull, the P-700 granite missiles had to be addressed. These are massive, 10-meter-long weapons designed to fly at Mach 2.5. They are powered by a liquid fuel rocket booster and a turbojet engine. The concern was twofold. To 1. Chemical volatility. The liquid fuel and oxidizers in the missiles are highly corrosive and toxic. After a year of immersion and the shock of the explosions, there was a high probability of leakage. 2. Warhead stability. The 750 kilograms conventional warheads use high explosive compounds that can become sensitive or weepy over time when exposed to seawater and temperature fluctuations. Russian ordnance experts had to board the rusted hull and manually inspect each of the 22 remaining silos. The silos were angled at 45 degrees along the sides of the ship, many of them deformed by the secondary blast. Using specialized bracing, each missile was carefully extracted. It was a nerve-wracking process of metallurgical bomb disposal on a massive scale. The forensic evidence. With the missiles removed, the investigation into Russian physics versus reality could begin. The primary goal was to determine exactly why the Kursk sank. For months, Russian officials had floated theories ranging from a collision with a U.S. Los Angeles-class submarine to the Kursk hitting an old World War II mine. The forensic evidence in the dry dock told a different story. Investigators found that the practice torpedo, a Type 6576 kit, had leaked high-test peroxide, HTP. HTP is a highly concentrated bleaching agent used as a propellant. When it comes into contact with copper or silver, it undergoes a violent exothermic reaction, expanding 5,000 times in volume. The resulting fire in the torpedo room reached temperatures exceeding 2,700 degrees Celsius, causing the simultaneous detonation of 5 to 7 other warheads. The force was so immense that it didn't just blow the bow off. It sent a supersonic shockwave through the air conditioning ducts, instantly incapacitating the crew in the forward 5 compartments, the human element, and the 9th compartment. As the ship was drained, recovery teams entered the 9th compartment at the very rear of the sub. Here, they found the final, heartbreaking proof of the crew's resilience. 23 sailors had survived the initial blasts. They had gathered in the stern, led by Lieutenant Captain Dmitry Kolesnikov. A note found in Kolesnikov's pocket provided the exact timeline. They had survived for hours in the dark, breathing through chemical oxygen generators. The data recovered from the hull proved that the Russian Navy's initial claims that the crew died instantly were a fabrication to mitigate the political fallout of the failed rescue attempts. The legacy of the lift. The salvage of the Kursk cost over $65 million, a staggering sum for the Russian Federation in 2001. But the value of the data recovered was immeasurable. It forced a total redesign of the Russian torpedo programs and led to the decommissioning of HTP-based weapons. More importantly, it redefined what was possible in subsea recovery. The impossible physics of the 9,000-ton lift had been conquered through a combination of Dutch hydraulic ingenuity and the sheer necessity of preventing a nuclear disaster. The Kursk was eventually towed to the Nerpa shipyard, where its reactors were defueled and the hull cut into scrap. The sail of the Kursk now stands as a memorial in the city of Murmansk. It serves as a reminder of the 118 men lost and the international team of engineers who defied the odds to bring them home. proving that even at the bottom of the Barents Sea, the laws of physics are merely a challenge to be solved. The successful docking of the Kursk was not the end of the operation. It was the beginning of a dangerous, multi-year decommissioning process that would test the limits of nuclear waste management. While the world's media moved on, the engineers at the NERPA shipyard faced a grim reality. They had a shattered, 9,000-ton radioactive jigsaw puzzle sitting in their dock, and every cut into the steel carried the risk of environmental catastrophe. The nuclear heart. The most critical phase was the defueling of the two VM4 pressurized water reactors. Each reactor contained approximately 480 kilograms of highly enriched uranium-2, 3, 5. During the lift, the primary concern was structural collapse. Now, the concern was long-term stability. Seawater is incredibly corrosive to nuclear fuel cladding. For over a year, the reactor core had been submerged in salt water that had breached the secondary containment systems. This created a high risk of corrosion-induced criticality. If the fuel rods had degraded sufficiently, moving them could trigger a chain reaction. To mitigate this, Russian nuclear technicians used a specialized dry extraction method. The reactor compartment, the fifth compartment, was physically cut out from the rest of the submarine's hull. This 1,000-ton section was then isolated and sealed with a special polymer coating to prevent any aerosolized radioactive particles from escaping. The fuel was eventually extracted using remote-controlled manipulators, a process that took months of painstaking, millimeter-by-millimeter work. The missile silo forensics. While the reactors were being neutralized, metallurgical experts were dissecting the P-700 granite silos. These shipwreck missiles are a marvel of Cold War engineering, designed with an onboard artificial intelligence meant to communicate between missiles in a swarm. The investigation revealed a terrifying detail. The blast from the torpedo room had been so powerful that it had deformed the armored hatches of the missile silos. Some of the missiles were jammed into their tubes with thousands of tons of pressure. Engineers had to use cold-cutting techniques, using high-pressure abrasive water jets to slice through the silo walls without generating the heat that could detonate the missile's solid fuel boosters. This was some of the most high-stakes demolition ever performed in a shipyard environment, as a single spark could have leveled the entire NERPA facility. The failure of Russian physics. The salvage of the Kursk ultimately debunked a long-standing myth within the Russian naval hierarchy. For decades, the Soviet and then Russian naval academies taught that the Oscar II's double-hull design made it unsinkable from internal accidents. They believed the volume of the inter-hull space would dissipate the energy of a torpedo detonation. The wreckage proved the opposite. The inter-hull space actually acted as a shaped charge corridor. When the second, larger explosion occurred, the simultaneous detonation of 7 torpedoes, the energy didn't just go out. It was channeled along the length of the ship between the two hulls. This piston effect is what caused the catastrophic failure of the bulkheads as far back as the reactor compartment. It was a failure of theory that led to the deaths of 118 men, and it forced the Russian Navy to completely overhaul the structural requirements for their next generation of submarines, such as the Borei and Yasin classes. A silent memorial. By 2003, the Kursk had been reduced to its constituent parts. The high-grade steel of the pressure hull was melted down and recycled, but the conning tower, or sail of the submarine, was saved. It sat for years in a scrapyard until a public outcry led to its restoration. Today, that sail stands in Murmansk, overlooking the Kola Bay. It is not just a memorial to the sailors, it is a monument to a mission that defied the limits of maritime engineering. The salvage was a rare moment in history, where Western commercial expertise driven by firms like Mammoth and Smith was used to secure a Russian nuclear asset. The recovery of the Kursk remains the benchmark for heavy-lift salvage. It proved that with enough hydraulic power, a sophisticated heave compensation system, and the courage to weld lifting plugs onto a nuclear tomb, no weight is too great to be moved. The 9,000-ton lift didn't just recover a ship, it recovered the truth of what happened on the 12th of August 2000, ensuring that the legacy of the Kursk would be written in facts and physics, rather than propaganda and silence.